Chapter 16, Part 2 notes, Climate, Topography, and Atmospheric Processes. The first thing we're going to talk about is temperature inversions. Normally in our atmosphere, as we increase in height, temperature decreases. When you climb up a mountain, it gets colder the higher you go. A temperature inversion, however, reverses the process. Temperature inversions are when warm air overlays cooler air and traps it underneath. This is created when a cold front is able to slide under a warm air mass. This usually happens when the cold air slides down a mountain slope and displaces by pushing up the warmer air. This is common in valleys and basins. This process then prevents convection currents from dispersing pollutants and traps them within the valley or the atmosphere. Temperature inversions can be called stable inversions when they happen rapidly at nighttime with cooling in a valley or basin, which creates the inversion instead of the cold air mass sliding down. The morning sunlight then absorbs concentrated aerosols in the colder air closer to the ground, which results in hazardous chemicals and creates smog. This is also a cause of ozone creation in our troposphere. A good example of a stable temperature inversion is Los Angeles. The clear sky at night allows for rapid cooling and heat loss on the surface, which then leads to a temperature inversion, which in the morning creates photochemical smog that surrounds the city. Wind-carried pollution. Some cities experience something like a temperature inversion because they have tall buildings that trap dust and contaminants and create what's called a dust dome, which changes the temperature within the city. Contaminants carried by wind can be carried to areas with no pollution as well. 70% of the mercury in the U.S. comes from an Asian source of pollution. Another pollutant that comes from Asia is the Asian brown cloud. This doesn't reach the U.S., but it does have effects on the El Niño weather patterns that we can see on our west coast. The Asian brown cloud is a 3-kilometer thick cloud that rests over the Indian subcontinent for most of the year, but eventually it will be pushed out into the Indian Ocean. This is where it cools and then has effects on the different ocean patterns. Another way that pollution is carried is called grasshopper transport or atmospheric distillation. This is when pollutant compounds evaporate from warmer areas and then move through the atmosphere with wind currents to a cooler area where they then can be deposited in the form of rain. Stratospheric ozone. Ozone in the stratosphere is a positive thing for Earth's living organisms. It traps the UV radiation, not heat radiation, but the kind that leads to skin cancer in humans. It's stated that if we lose 1% of our ozone, it could potentially result in an extra million cases of skin cancer per year. Stratospheric ozone does have a natural change. Every September and October, due to Antarctic cold temperatures, the circumpolar vortex is a wind system that creates a drop in stratospheric temperatures. This then creates ice crystals in the stratosphere, which lead to the breakdown of ozone. Ozone will naturally reform as the stratospheric temperatures increase after the winter. Stratospheric ozone depletion. This was first noted in the 1960s and then became a real concern around 1985 when a scientist decided that this was a problem, creating an ozone hole. An ozone hole is the term for the depletion over the South Pole, but it's now being noted that we also have an ozone depletion over the North Pole as well. These depletions are caused by human causes such as chlorine-based gases. Now remember, there are naturally holes caused by natural occurrences, as in the temperature drop, but we're now increasing this hole, just as when we add to pollution it increases it and causes an exponential decay in result. The main gas that causes ozone depletion is chlorofluorocarbons. This was used in industrial gases, refrigerators, air conditioning units, styrofoam manufacturing, and aerosol sprays from the 1930s to the 1980s. CFCs have been phased out in developing countries, however, so that this is a lessening problem. The Montreal Protocol of 1987 is the response to ozone loss, which called out the phasing of CFC use. Developed countries were forced to phase out CFCs, while developing countries were able to purchase credits to continue using CFCs until they developed better technology. This program for developing countries is now being phased out as we would like to eliminate all use of CFCs in the planet. The CFC production since 1988 has decreased by 95%, so most of the goals of the Montreal Protocol have been met. Substitutes like hydrochlorofluorocarbons, HCFCs, which release less carbon or less chlorine into the atmosphere, have been developed. And studies are suggesting that ozone recovery should occur by 2049. Now, why isn't the ozone recovering faster? If we've stopped using most CFCs since 1996, then how come we still see this problem of ozone depletion increasing? Well, CFCs take up to 5 years to reach the stratosphere, and then when they get there, they don't degrade very quickly because they're a human-made compound. This means that they continue to affect ozone in the stratosphere for a long time after they're released. Also, the ozone does take a while to rebuild, and this process isn't being helped by global warming, which is creating warmer tropospheric temperatures. These warmer temperatures in the troposphere are leading to cooler temperatures in the stratosphere. If radiation of reflected and re-radiated heat from Earth's surface is being trapped more likely in the troposphere by greenhouse gases, then less of that radiation is reaching the stratosphere, thereby cooling the temperatures. And we remember, as noted, that the natural cause of stratospheric ozone depletion is a temperature change. I have 2 additional resources that you may want to read about CFCs and ozone depletion. This will help you in a free response that you will complete later this week on ozone.